Alright, so this week we're going to be taking a look at vectors. So it'll be all the same section, section 8.5. A little bit of application. We're going to do a lot of sketching today, so that's a good way if you've never done vectors to kind of visualize how they work. But we're going to eventually get away from sketching, because sketching's good, like if you get to see how it works and you have a word problem. But in general, if you want to be able to do things faster with vectors, sketching is not always the fastest. Okay, but it is good to start out. So a vector is basically a quantity that we're going to use that describes two things at the same time. It describes what we call a magnitude and a direction. So anyone that is in physics, can you give me an example of a quantity that a vector would be good to describe? Yeah?
You could say maybe a force.
A force, yep, that's perfect. A force is definitely a vector because it has two parts to it. You have a magnitude, which is the strength of the force, like how hard you're pushing or pulling on something, and then there's the direction. Okay? Which way you're pushing down, you're pulling up, what are you doing? Yep, so force is a good one. And anybody know, there's one other real common one that we can use a vector for? Yeah?
Velocity.
Yep, velocity. So velocity also has a magnitude. With velocity, the magnitude would be the speed, like how fast something's going, and then what direction is it going in. Okay, we might describe that direction with a compass, like as degrees from north. We're going to mostly be doing two-dimensional word problems with velocity, so we can kind of describe it as up, down, left, or right, things like that. Right. And then just kind of looking a little bit more at the velocity example, we could look at that picture, and each one of those planes we could think of as a vector. Okay, they all have a magnitude and they all have a direction. So if we click on one, we should be able to see, hopefully. All right, so this particular plane is going from Boston to Pittsburgh. So the direction we would expect to see is mostly west. When it takes off, it might go a little bit north or south. Pittsburgh is south of us, so it's going to be a little southwest. But it's mostly west. And then when we think about what direction west is, we got to be careful because we don't use the same angular system that a compass uses. So for us, we have 0 degrees at the right whenever we do our axes. On a compass, 0 degrees is north. So as far as west would be 270, right? So we would expect to see a lot of numbers around 270. So let's look at the direction and see if we can see some numbers in the 200s. A lot of them around 200, 260s, 250s, 240s. Right, so all those are the directions. Now this is a little more complicated vector because the direction is constantly changing. Which is fine, but our directions are going to stay fixed and they're not going to change throughout the problem. Okay, so that's the direction and the magnitude of the plane. Well, if we click, actually it wasn't going to do this. Back on the other page, that would be the speed. So it tells us right here the speed is right now 444 miles per hour. So it has a magnitude and it has a speed. And then for all these planes, it's the job of the air traffic controller at each airport to make sure that all those planes stay spaced out. And we can look at all those as vectors, and a computer helps them to keep everything separate. Even two planes that look very close, remember we're zoomed out pretty far, those planes could be 30 or 40 miles apart, not even see each other. And they could be at different altitudes. So that's the other thing when we're dealing with 3D, two planes that are maybe looking like they're on top of each other in 2D. One could be on the ground and one could be in the air. So that could be, that situation is fine. But that's a really good example of vectors. And if you want a high stress job, you could become an air traffic controller and coordinate all those planes. So one way that we can represent vectors when we're drawing them is with an arrow. So an arrow naturally works well for a vector because it has a point on it, so that can tell you the direction that it's going. And then what do you think we would do to the arrow to represent, say, a velocity vector where a plane is going slower or faster? What would change about the arrow? Yep.
Length of the arrow.
Yep, we can change the length of the arrow. So the length of the arrow will represent the magnitude. In the case of velocity, that's the speed. If it was a force, it would be the strength of the force. Now, one downside with drawing is if we have to, say, take out a vector, and let's say we represent a plane going 80 miles an hour, and then we have to represent a plane going 600 miles an hour. Well, we've got to draw that vector 7 or 8 times as long as the original. So depending how much room we have, if you have to make something 8 times longer, that could take up a lot of space. So we've got to kind of think about how we scale our axes and things like that. When we are drawing, generally we want to use some kind of grid. So I have graph paper in the back under the TV for homework if you need it. And the other thing we want to use is something that we can draw straight arrows. We want to make sure that everything looks good. All right, so vectors, they have a start point and they have an end point. They don't go on forever. Okay? If a vector went on forever, that would represent something like infinite speed, right? Or infinite force. We don't have that. So a vector starts at what we call the initial point, and it stops at the terminal point. Okay, so this particular vector starts at P, and it ends at Q. Now, when you draw a diagram, if you have lots of vectors in the diagram, like some of the homework problems or on the test, it can start to get a little bit busy with arrows, and it can be hard to tell sometimes where an arrowhead is and where it isn't. All right, so I'll try to make the diagrams as clear as possible. And if you ever had a question on a diagram, I would always clarify what the diagram is supposed to look like. Now, one way we can name a vector is just by a single letter. That's generally how they're named. But what do we already use single letters for in math in general?
Variables.
Right, we already use single letters for variables, and vectors are not variables. They're vectors. So if we're going to use a single letter to name it, we have to make the letter look different than a variable. And there's 2 ways that we can do it. One way we can do it is we can put an arrow above the letter. This particular arrow has nothing to really do with indicating the direction. This does not mean vector m points to the right. It just means m is a vector. Could point up, down, left, or right. But you always put an arrow on the top pointing to the right. Or you could just make the letter bold. Okay, and that's what our book does a lot. When you look at the homework tonight, you'll be able to tell it's a bold letter. Okay, so this particular vector is labeled M. English letter is generally what you use when you're labeling it. But there are a few letters that are kind of special. They're reserved letters we don't want to use. 3 of them are I, J, and K. So if you want to name a vector, just pick a letter besides one of those 3. And anything that could look like something you don't want it to, like the letter O, could look like a 0. So probably stay away from that letter too. All right, so I want to look at what happens when we add 2 vectors together. So what I want to do is kind of think of an example with force. So let's say we had like a boat right there. And there was a force acting that way on the boat. And then there was a force, let's do it like that, acting that way on the boat at the same time. Both of those forces are acting on that boat. Okay. What's going to happen when those 2 forces act on that boat at the same time? Like I'm thinking about like what direction is the boat going to move in? Yeah.
The boat would be moving mostly right, but they would have some upward direction. It would create one vector, because you can't go two different ways at the same time.
Yeah, so what's going to happen exactly is those two vectors are going to basically combine into one, and it's going to move on a diagonal. In fact, when we combine the two vectors, they would look exactly like this. That is the new vector for the boat. That's the direction it's going to move, and that is the magnitude if you measure the length. Okay? So notice it is more right than it is up, because the horizontal component, or the horizontal part of the vector, was longer than the vertical part, but it still is a little bit of a diagonal. So that's an important concept to understand. When you take two vectors and you add them together, the way that I just showed you, you get a new vector. Okay, so adding vectors results in a vector. And the way we're going to add them for today is I'm going to show you a visual method where you take two vectors and you stack them together, and then you draw in a diagonal. Do you add vectors like that in physics, or? No? Okay. Well, I'll show you how we do that. All right, so let's look at how we can add two vectors visually. So what we want to do is line them up so that the end of one vector lines up with the beginning of the next. Okay? So let me show you that step up above. So let's take a vector like this. Let's take a vector like that, and let's add them together. Let's call this one V. We'll call that one W. And when I draw a vector, again, it should be a bold letter. So I'm going to add V plus W. So that means start with V, take W, and line it up just like that. So position the vectors so that the end point of V and the terminal point of W line up. Okay. And then lastly, what I'm going to do is I'm going to draw the diagonal in from the initial point of the first vector to the terminal point of the last vector. Okay, so just like that. And that is a visual for V plus W. Any question how I line those vectors up to add them? Okay. So again, that does require a couple things if you're going to do it on graph paper to make it come out accurate so that we can look at it and actually measure it. We need to plan a little bit where we start our vectors, because if we don't, we could go off the graph paper. Right. The other thing is you can also do this for more than two vectors. If you had vectors like, you want to add all those vectors together, that's fine. You can take them all, and we could take this one, put on that one, do that one, we could do that one, and then we could do that one. There's probably a way I could have arranged them so they didn't overlap like that. We'll have to see if the order makes a difference. But ultimately, the final answer, when you add all those vectors together, start there, end there, that's the answer. Right, so when you connect your vectors, they should all be connected initial to terminal, and think of those arrows as making like a one-way path that like water flowing in a pipe would go. Right. You shouldn't have two arrowheads coming together, or two initials or two terminals. You should always be connecting initial to a terminal. Okay, let's try that on this one. There's only two vectors, and I can tell they both point to the right. So that means whatever I do for graphing, I want to start more on the left to give myself plenty of space. All right, so we're going to do V plus W. So start with V. Put that right there. Put W on the end, just like that. Okay, if that's all you do, you've lined them up, but you haven't given me the answer visually. So what do I have to do to finish that off and get the actual picture? Yeah.
From the start point of view to that.
Yep. Add in this vector starting at V, ending at W, and that's it. That is the answer. It's a picture. Right, so the picture is helpful because it does give you an idea of what direction the new vector is going to point in, and we can see that the new vector is a greater magnitude than either of the originals. It's much longer, and that's because these vectors are working together. Right? When vectors are not working together, the result can be shorter. I don't know when I added all these together. If it was shorter, no, it looks like mostly it is longer than all of the originals. But the result could be shorter. Any question on that? All right, let's look at this one. So they want us to add V plus W. And what's going to happen when we add those together? Yeah.
Those cancel out.
Yeah, it's kind of going to cancel out. So think about, you got to connect the end of V to the start of W. That's the first step. You have to line up those two purple dots. Once you do that, then you're going to connect the beginning of the first vector to the end of the second vector. So the goal when you're done is to connect the two green dots, but you line the purple ones up first. Well, if you line the purple ones up, and then look at what happened to the green ones, they also lined up. So for this one, there isn't really a picture we can draw, so we need a symbol. Well, what did we say happens when you add two vectors together? The result is always what? Yeah?
They cancel out.
Well, no, they don't always cancel out when we add two vectors together. In this case, they do. But what happens in general when you add two vectors together? You always what? What's the result? Yeah?
You always get a longer vector than the other.
You always get what?
A longer vector.
No, we don't always get a longer vector. Yeah?
You draw a line from beginning to end, and in this case it would just be like a dot.
Okay, so it's kind of like a dot. I'm looking for a single word. When we add two vectors together, what happens? We get, yeah?
A direction or a magnitude.
Yeah, a new vector. When you add two vectors together, you get a vector. Doesn't necessarily have to be longer. Doesn't have to be shorter. It could be the same. But you have to get a new vector. So the answer here has to be a vector. It's just a vector we can't draw. So we're going to call it the zero vector. So we can go like this. Or you could write it like that. So this is the zero vector. Okay, when you have the zero vector, it doesn't mean that there's no force involved. It just means the forces are canceling each other out, and in this problem, everything is balanced, right? In fact, that's what happens most of the time when there are forces. Everything is balanced, right? This board isn't moving because it's balanced. It's screwed to the wall, so whatever force is trying to pull it down, there's a force pulling it back up. It's not moving. If you had like a tug of war, right? Think about what would happen if you had a lot of people pulling on each side and the rope's not moving. It doesn't mean that there's no tension in the rope. There could be no tension if the rope's not moving, but there could be a lot of tension in the rope. It's just balanced. Because if you cut the rope in the middle, everyone would fall because there's so much tension in the rope. Okay. Any question on that idea? So it's called the zero vector. So when I added all those vectors together, I might have mentioned something about the order, and we'd have to see, does that make a difference? And the answer is no. It doesn't matter how you add vectors together. You can switch the order, and you will always get the same answer. Okay? So vector addition is both commutative, which means you can switch the order, and associative, which means you can change the grouping. Okay? So let's look at an example. I'm not going to do 5 vectors like I did before. I'm just going to do 2. And I'm going to show you if I switch the order that I add them up in, I get the same thing. Okay, so the first way that I'm going to do it is V plus W. That means start with V and put W on the end. Like that. That's V plus W. Let's draw in the diagonal. Okay, I'm just doing this by eye, so I don't have any graph paper. I mean, my lines are straight. But I'm not using a grid, so it might not be perfect, but it's pretty close. So any question how I got V plus W? Okay, now I'm going to switch it, and I'm going to start with W. I'm going to put V on the end. Okay, that's W plus V. Now if I draw in my diagonal, so that's W plus V, and now I want to line them up and see how they compare. Let's see. A little bit off, not bad, it's pretty close. Right, but that's W plus V. Okay, so they should be identical. So that's the commutative property. And that works for 2 vectors, it works for 100 vectors. You can always add the vectors in any order, and the result will be the same. Now associative. So with associative, notice there's no change in the order. Both the orders are ABC and ADC. What's changing is what I do first. Okay, so on the left side, they're going to have me add the A and the B first, and then I'll add C to that. Okay, so let's do A plus B. You know what? I want to make this just a little longer, because I don't want my vector to be close to horizontal, and that would have been, because I can't draw. If something gets really close to horizontal, it doesn't let me go in between. It just kind of snaps in place. So that would have been hard for me to draw. So that should be fine. All right, so that's A plus B. So put that back there. All right, so now I've got that part, and now I'm going to add C onto the end. So let's add C, like that. And now connect the beginning to the end. Okay, so that should be A plus B plus C. Put that back there. Okay, any question how I got the first one? Okay, so let's do the same thing on the other side, but we're going to start with B, and we're going to put C on the end. Okay, so that's B plus C. So draw that. And the arrowheads are kind of different sizes, so I'm just doing the best I can with it. All right, so I got B plus C, and now take A and put what we just did on the end of that. So here's A. Put that on the end. Draw in our diagonal. That is A plus B plus C. And if I line them up, pretty close. They come out the same. So both addition and subtraction. Well, addition works with commutative and associative property. Okay, we are going to look at subtraction in a minute. And we're going to start by thinking about this idea. What would be the difference between the vector v and negative v? Yeah.
The direction.
Yeah, it would just be the direction. That's the only thing that would change. Okay. What would be the same between those two vectors? Yep.
The magnitude.
The magnitude. There's no difference in the magnitude. They just are pointing in different directions. Specifically, exactly opposite directions. It's like they're 180 degrees rotated. And this is an example of what we just saw a couple problems ago, where you add two vectors together and they cancel out. Well, this is what we just did. We added a vector to its opposite, and we got the 0 vector. So now I want to think about how we could subtract two vectors. Anyone think they could tell me how I could rewrite that subtraction problem so we could add the two vectors together using what we just learned? Yeah?
V plus negative W.
Exactly. We could take V, and instead of subtracting, which I didn't really teach you how to do subtraction visually, because we don't have to do anything different. Instead of adding the original vector, we're going to take the opposite of the second vector, and that is going to make it subtraction. So it's the same way you could do it with numbers. If you don't understand how to do 2 minus 3, you could do 2 plus the opposite of 3, and you get the same result using addition with a negative. So that is how you subtract two vectors. Take the second vector, find the opposite of it, and then add. Okay, and for us, finding the opposite of a vector means to take your vector and have it point the other way. Keep the length the same, just flip the direction. All right, so let's see if we can subtract two vectors visually. Okay, we will get into doing it with numbers in a little while, probably more tomorrow. Okay, so they want us to do V minus W. First thing is we're going to rethink how to do V minus W in a way that works method of doing it visually. So instead of V minus W, what are we going to have? Yep.
V plus negative W.
Okay, so the first thing I need to do is figure out negative W. Well, I can do that on the smartboard exactly. Anyone have a guess how I could make that point the other way? I don't have a rotate 180. I don't have that option on here. But there is something else I could do that's equivalent to rotating at 180. Yeah?
If you were to flip, you should be able to mirror it.
Which way?
Left, right.
Let me make a copy of it so we don't do the original. So flip it left, right. Okay.
And then you'd also flip it up, down.
And flip it up, down. If you do two reflections, a horizontal and a vertical, that's the same as rotating 180. Okay, so that is an exact copy of W pointing in the opposite direction. All right. Now take V and add negative W on the end. So here's V. There's negative W. And connect just like that. And that's V plus negative W, which is V minus W. Okay. So any question on adding vectors or subtracting vectors? Okay, so the next thing we're going to look at is taking a vector like that, and maybe doing something like that to it, or even something like that. Anybody know what it's called when I take a vector like the one I started with here and change it into either that one or that one? What am I doing to the original vector in those other two examples? how do these two vectors compare to the first one? What's the difference between this one and that one? Well, we're in, yeah.
One is stretched, another one is compressed.
Yeah, so we're lengthening and shortening the vector. Okay. So that's an operation we can do. Not necessarily, I mean, you can do it with addition. If you add a little bit of a vector that points the opposite way of your vector, you could try to compress it. But an easier way to stretch or compress something is what we call scalar multiplication. So think about what it means to scale something. Like if you build a scale model. A scale model could be bigger or smaller, depends what you're making a model of. If you were making a model of like a cell, you're probably going to make a larger diagram of cell structure. If you're making a scale model of a house, you're probably not making it larger than the house. You're probably making a smaller model so you can see what it would look like. But either way, you're changing the size. Okay, so you're not changing anything else right now, just the size, longer and shorter. And the way that this looks is when you put a number in front of a vector. That's an example of what we call a scalar product. There are three kinds of products we're going to talk about this week. That's the simplest one, scalar product. The next one we're going to talk about on Wednesday is dot product. And the last one we'll do on Thursday is cross product. So if somebody just said to you, explain how you do multiplication when you're working with vectors, well, that's a very vague question, because there's three different ways to do it, so you have to know which way are they talking about. Okay. So when you scale a vector, the result is another new vector. It could be longer, it could be shorter, but there's one more thing that could happen. We didn't mention it. What else could happen when you scale a vector? Besides getting longer or shorter, don't scale by 0. That would wipe the vector out completely. And scaling by 1, technically it would stay the same. So no, I'm not talking about that. But what else could happen besides longer or shorter? Yeah?
If it's like a negative number, you change it.
Right. If you have a negative number, it could change the direction. It could reverse the direction. So that's the only change that can happen with a scalar product as far as direction. It could point exactly the opposite way if you multiply by a negative. So that's called a scalar product. So the thing with scalar products is you can get vectors that start to get really big. So if you don't plan appropriately, you can go way off your graph paper. Alright. So now they want us to find two scalar products, 2v and 1/2 v. All right. What? How can I find 2v exactly? And I don't want to use a ruler and measure anything. I just want to find exactly 2v. So what could I do? What?
Could you like just double the original vector?
Yeah. How would you do that? Like on the board visually, what would I do?
Or is there a copy option?
Yes, there is.
I guess you would use that and you would put the start point, the end point of the new vector onto the start point of the old vector.
Yeah. So we just have to make two copies of them and add them together. Okay, so we'll take that vector, copy it, and put them together. And don't forget to draw your final answer. So that is the vector 2v. Now, to do 1/2 v, I don't really have a way I can do that on the board without measuring. If I could scale it by like 50%, I could make it smaller. But I'm going to have to just estimate that one. 1/2 V, I don't know, maybe about like that. If I was using a grid, then I could do it exact. Just measure the distance and do it half as long. Okay, so no change in the direction, just changes in magnitude and height. Questions on that? All right, let's try this one. What's going to happen when I do the scalar products here compared to the last example? What's going to be different? Yep. Right, they're going to change direction. So the first one, I put -1v. That's the same as just -v. So for that, we can do it exact. I'll just take and flip it twice, horizontally and vertically. And that gives me a perfect copy of v, same length, pointing the other way. For the -1/3 v, again, I don't really have a way to do that unless I use a grid, right, to measure it. But I've already got v flipped, so that's the negative, and just make it 1/3 as long. So I'll just estimate maybe about like that. Okay. So any question on finding a scalar product where the scalar is a negative? Okay. So now, before I think the last thing we're going to do visually, I want to combine a scalar product with addition and subtraction. Let's do the second one. I mean, it doesn't matter, but let's do one that has addition, subtraction, and a scalar all in the same problem. Okay, so what's the first thing that I have to do here? To find 2v minus w plus u. Okay, let's start with 2v. So again, v is up and to the right. W is going to, when we flip that around, go to the left. But u is also up and to the right. So I have a lot of vectors that are going right, so I'm going to want to start closer to the left edge. So let's make 2 copies of that and add those together. Okay, so there's 2v. What do I need to do next? Yep, Jackson.
Flip the W vector.
Yep, so I'm just going to do this by hand because it's a little quicker. Okay, so there's W, and I flip the direction, so that's going to go right about there. So now I've got 2v minus W. And Vanessa, what do I need to put on the end of that? U. So let's take U. Let's copy it, and we'll put that right there. Okay, so there's the visual of 2v minus w plus u. And my last step.
I mean, your last step would be to draw the composite vector, the vector that's made of those.
Yeah, yep, draw that in.
Yep.
Yep.
I guess.
So just make sure you start here and there. And there you go. 2v minus w plus u. So any question on that? Yes?
There's a small question. For the equation, would you have to change 2v minus w to 2v plus negative w, or is that not necessary at this point?
Oh, you mean just rewriting it?
Yeah.
No, you don't have to, because this one was more about the visual. So if you wanted to explain to somebody what this visual means, yes, technically it's 2v plus negative w. That's how you could explain it using all addition. But the picture we've drawn is accurate, and we drew the final answer accurate, so that's what they were really looking for. Yeah. Okay, so again, drawing's fine, but for everything we've done so far, it wasn't really necessary. Yeah, gives you a good visual. You can see the resultant vector or the composite vector really well, but it's not always the fastest method. So we're going to start talk about other ways we can do things with vectors that are more numeric and less visual. Okay, and when we see a symbol like this symbol is a good example of that. So when you put double bars around a vector, it means magnitude. And when you find the magnitude of a vector, what kind of answer do you get? Like when you add two vectors, the kind of answer you get is a vector. When you subtract two vectors, the kind of answer is a vector. How about when you find the magnitude of a vector? Yeah?
You get a number.
You get just a number, single number, 13, 16, 14.2, just a single number. But we could be a little more specific about the kind of number. Anybody think they could be a little more specific than just a number? Yeah?
Well, if it's force, you can put newtons. Or
Okay, so it could have a label on it, but something that we don't, not a label, just as far as a type of number, like in math. Yeah?
Real number.
No, we can't get any real number for the magnitude. There are real numbers that would not make sense for magnitude. Anyone think they can tell me what kind of number we always have to get? Yeah, positive. It has to be positive, right? Because it's magnitude. There's no such thing as when you're talking about the speed of an object, you don't have negative speed. Okay? You could have direction south instead of north, but that doesn't mean you're driving negative speed. You're going in a different direction. Okay? So the magnitude of a vector is always positive. And if we look at, we're going to do more of this tomorrow, but if I just put this vector, let's try to put it as nice as I can. How could you find the length of that vector? It's not horizontal or vertical, so you can't just count. It's on a diagonal. Yeah?
Pythagorean theorem.
Yep, we can use Pythagorean theorem. So tomorrow we'll look more at how we can find the magnitude of that vector, but it's just going to end up being Pythagorean theorem. Yep. Okay. What would be the difference between those two quantities? The magnitude of v and the magnitude of negative v. Yeah.
Would they just be the same?
They would be the same. Yep. A lot of times an answer I get is, well, they point in different directions. Well, that's not what I asked. I asked, what's the difference between the magnitude of v and the magnitude of negative v? And the answer is nothing. They are the same thing. So if a vector happens to have a length of 1 unit, that vector is called a unit vector. Okay, so we're using the word unit there the same way we used it when we did unit circle. Okay, we talked about circle with a radius of 1. We're talking about a vector with a length of 1. Okay, it's called a unit vector. And we're going to talk a lot about unit vectors tomorrow. Now, this doesn't really require a visual. If you want to find the magnitude of a vector, if you give me the vector as a visual, then yes, I would have to draw a picture and make a triangle and do Pythagorean theorem. But if you could just give me the vector as numbers, then I could just do the Pythagorean theorem as a formula without even drawing a picture to find the magnitude. I would just need to know how far left and right did you go. Like I would need this number along the bottom, and I would need that number for the height. If you just told me those two numbers, that's all I really need to know to describe a vector. The horizontal distance and the vertical distance. And that's the first way that we're going to look at how we can describe a vector rather than drawing. This notation our book calls an algebraic vector. Looks kind of like a coordinate, but a little bit different. We've got these angle brackets. I guess if you were doing it on the computer, it would be like a less than and a greater than. think those symbols would work? And we put two numbers between them with a comma. Okay, the two numbers represent what we call the components of the vector. What they really represent, if you made a triangle out of the vector, the base of the triangle and the height of the triangle. So you can kind of think of the A and the B as directions. Starting from somewhere, say we start right there, A tells you from that point how many units you go left or right. Left would be a negative value for A, right would be a positive value. And then B tells you from right here how many units you go up or down. If B is positive, you go up. If it's negative, you go down. So it's directions from the start point to the terminal point along a horizontal and vertical path. That's what A and B are. Just like that. So let's look at this vector 2, 3. So it's directions. It tells me to go a certain number of units left and right, and then a certain number of units up and down. But this doesn't tell me something about the vector. So this information right here describes what this how this notation works. But what does that notation not tell you about the vector? Yeah?
The initial point.
It doesn't tell you the initial point. You can put the initial point wherever you want. So if they said to draw the vector 2, 3, perfectly fine way to do it is what I just did on the board. That is the vector 2, 3. As long as you go right 2 and up 3, you've correctly drawn the vector. We could put it over here. Go right 2, up 3. You can put it over here. Anywhere you want to draw it. Now, even though you can draw it anywhere, there is a place that's most common to start from. Anybody have a guess where the most common place we would start from is? Yeah?
The origin.
Yeah, the origin. Okay, if I had a choice of where I could start from, most likely I would start at the origin. And when it starts at the origin, that's called a position vector. So again, that notation doesn't tell you where to position the vector in the plane. But if I asked you to draw something as a position vector, then I have told you where to start from. Okay? So you need to know that a position vector starts at the origin. So what I want to look at lastly is how could we take one of those vectors and figure out the 2 and the 3 if all they did was give us an initial point and a terminal point? What if they just gave us coordinates? How would you figure out the 2 and the 3? So let's look at that. Okay, let's write down the coordinates of, I could do any of these vectors, but let's do the one in quadrant 1. What's the coordinate of the initial point? Yep. 6, 2. All right. And what's the coordinate of the terminal point? Yep.
8, 5.
8, 5. So the goal now is pretend you don't have the picture. All you've got is that. You've got 2 points. This is the initial. This is the terminal. If I just gave you those 2 points, does anybody see how you could change those 2 points into that vector. So it's like we kind of work backwards. Yep.
Subtract the terminal from the, or subtract the initial from the terminal.
Subtract the initial from the terminal. Terminal minus initial. Okay, that will give you, and I'm going to write that nicely on the next page, but that will give you the position vector. It has to be terminal minus initial. If you flip the order, we know subtraction is not commutative, you're going to get a different answer. Okay. But in this case, 8 minus 6, that's how you get the 2. And 5 minus 2 is how you get the 3. So this is called finding a position vector. Okay, in order to find a position vector, I have to give you the 2 points, just like the example. If I don't name one of them as initial and terminal, okay, like here I did, initial and terminal. But if I don't, you always assume that P1 is the initial and P2 is the terminal. And to convert that into a vector from its initial point and terminal point, subtract terminal minus initial for the x's and terminal minus initial for the y's. And that will change it into a vector. Now, this notation that we're using to write vectors like this, that is not the only way to write a vector without drawing. Okay, there is another way, and we're going to look at that way tomorrow. So we'll do an example of this, but part of the homework is going to say to do something that I haven't taught you yet. So I'm going to change the directions on a couple of the questions. So make sure when you write down the homework, you copy down the directions that I change as well. I'll put them on the board. Okay, so here's our points. And let's see if we can find the position vector. Okay, what's going to be the calculation for the horizontal component of my vector using that initial and that terminal point? Can you tell me the calculation?
4 minus negative.
Okay, so we're going to do 4 minus negative 1. Good, which will simplify to 5. We'll do that in a second. And what's going to be the calculation for my vertical component? Yeah, 6 minus 2. So now we'll simplify it. 5, 4. So if I wanted you to draw that as a position vector, that means you would start at the origin and you would go 5 units right, 4 units up, put your dot there for the terminal point, and connect the initial to the terminal, and draw your arrow in that direction, from the origin to your point. Hey, any question on that? Now, I've also been using the words horizontal component and vertical component. And that works fine when we're doing 2D. Horizontal is left and right, vertical is up and down. When we get into 3D, I have to kind of get away from using those words because in 3D it's a little more complicated. So we're going to start to refer to this as the x-axis component and the y-axis component. So that way we don't have to think about in 3D, wait, which way means vertical. Okay. All right, so that's the first part on vectors. Right, so tomorrow we'll continue, same section. It is going to say 5.4. I know I called it lesson 8.5 because I just use the lessons your book uses for the number. But the PDF is on Schoology in the 8.5 part 1 folder. The lesson I showed you at the beginning of the class. Okay, so 1 through 10, all 14 to 22 even. On the 26 to 32, they're asking you to do a couple things. You're not going to be able to do the second thing because I haven't taught you how to do it yet. Unless you already know how to do it. but just find the position vector on 26 to 32. All right, you've got about 15 minutes. So please use the time to try to get a little bit of something done. Also, I will be after school this week on Thursday.